So today we'll have Arian Maleki tell us about stochastic gradient methods.
Sure. Okay. Hello, everyone. Let me make a few points before I start about this presentation. The first thing is that I'm not an expert in the area, right? So the reason I decided to, I volunteered to present this thing was that I wanted to learn the topic, and I thought it's a good idea to block 1 week and then just learn about this stuff. So the reason I'm saying this is that if you're an expert and you have done research in the area, then it doesn't have probably anything for you. And the intention is mainly for first year, second year, PhD students, master students. And that's going to be more or less the level of the talk. And then, but if you're an expert and you're here and you feel like I'm saying something wrong, please feel free to interrupt me and let us know. It will benefit me and everyone else. So with this introduction, let me start. I'm going to start with a little bit of convex optimization because I'm going to use some of these results later. And just to make sure that we are on the same page, I'm going to review some of the basic stuff for, let's say, 20 to 25 minutes, and then we go to the stochastic gradient descent. Okay. So one of the basic and simple problems in convex optimization is that, I have a function f of x, and let's say this function is from Rp to R. Everyone can see what I'm writing, right? It's not too small or too big, okay? What's that? Oh, really? Okay, so let me, I guess can we? It's better? Okay. So this is a function, and let's say it's a convex function. So whenever I'm talking about convex function, you want to remember bowl-shaped functions. So this is a bowl-shaped function, and we want to minimize f of x for x. This is kind of the simplest convex optimization problem that we have. And whenever you want to find the minimizer of this function, you have to make certain assumptions about this function, right? Beyond convexity. So beyond convexity, you have to make some assumptions about the function f, and that is the type of calculation you can do with this function, right? So in for example, one idea would be what we call first order oracle. We assume that we can efficiently calculate the gradient of the function. So in this talk, I'm going to assume that the function is differentiable. If it's not differentiable, you can, most of the ideas are going to go through anyway. So we can efficiently calculate the gradients of this function at every point. So if you give me x, I can return you a gradient of f of x. And efficiently, of course, depends on your application. How much computation you are willing to have with this function. And if this is efficient, then we can say, OK, gradients can be calculated. Then the idea is that once we have these first order oracles based on like the gradient information, how are you going to get the minimizer of the function x? Of course, you can go beyond this and say, I want to have, let's say, second order oracle, right? Like in my application, not only I can calculate the gradients, but we can efficiently calculate the gradient of f at x and also the Hessian of the x. And then the game has changed now, right? In here, the only algorithms I can do are the algorithms that are using the gradient information. And then in here, I'm allowed to use algorithms that can do both gradient and Hessian and use this information. Okay, for most of the talk, I'm going to focus on first-order oracle. In machine learning, as we will see later, most of the things, calculating the gradient and stuff is easy, and we can do it in many cases. But in many cases, calculating the Hessian is quite complicated. So it takes a lot of time, and we prefer not to use the Hessian information. But later, if I have time, toward the end of the lecture, I'm going to go back to second-order oracle and see what they can offer to us, both in terms of the deterministic settings and stochastic settings. Okay, so let's focus on the first-order oracle. I'm going to write it here. And okay, so what we have here is the gradient information. And from the gradient information, I want to calculate the minimizer of the function. The idea is very simple, and it goes back to Cauchy back in around 8050. The idea is that if I'm at this point and I calculate the gradient is going to be more or less positive. So it's going to say, if you move in this direction, the function is going to increase. So I can, in order to reduce the function, I can move in the direction of the negative of the gradient. So this is the gradient descent idea. So gradient descent is probably the most natural algorithm that you can think of, and most of you have heard of. Says that, I'm going to start from, I have an iterative algorithm. I start from xt, and then my next iteration is going to be xt minus alpha t, that we call it a step size. It's just a real number, a gradient of f at point t, at time t. Okay, so this is the gradient descent idea. Goes back to Cauchy, very old idea and very useful. Many people have used it. Now that we have this algorithm, we have to ask several questions about our algorithm, right? So let's say, suppose f has a unique minimizer, x star. So then the first question that you would like to know is whether I'm going to write them here, does xt converge to x star? The second question would be, what is the convergence rate? And of course, the third question that is also important is whether this is an optimal algorithm, right? So is this the best algorithm that I can come up with based on gradient information, right? So I only have access to gradients. Gradient descent seems to be a reasonable algorithm, at least from the intuition here. And then the question is it optimal? Can I make sure that every other algorithm that uses gradient information is going to perform worse than gradient descent or not? So that's what we want to. These are the basic questions we want to answer about the gradient descent. Any questions so far? Yes.
Sorry, could you clarify your definition of optimal?
I'm going to get to that. I'm going to mention it later. But intuitively, it should be clear, right? So it has a certain convergence rate. It goes at a certain rate to x star. Is it the fastest rate we can get? So, I'm going to define it more formally later. So let me start with a very simple example, but then you will see that to talk about the first two questions. I'm going to first talk about the first two questions here. I'm going to start with a very simple example that we can easily see what is happening in gradient descent. And then I'm going to generalize the proof very fast, right? So the idea is the following, right? Okay. So let's study the convergence rate of the gradient descent. So convergence rate. of gradient descent. And I'm going to focus on a very simple example that gives all the main ideas that is here, and then we go to much more complicated, like the general setting. So the example is X transpose AX minus B transpose X, a quadratic function. Let's say A is positive definite matrix to make sure that this function is convex. And I want to use gradient descent to find the minimizer of this function that you already know if you take a derivative. Let me just put 1/2 here too. That you already know that if I take the derivative, it's going to be a minus 1b. But let's use gradient descent to get the minimizer. Okay? So what is the gradient descent? The gradient descent is very easy. xt plus 1 is going to be equal to xt minus alpha. And the gradient, right? So the gradient of this function is ax minus b. Axt minus b. Let's say this is my gradient descent algorithm. And I want to see how fast it converges to x star, right? So we know that x star, if you take a derivative, ax star is equal to b. So what I'm going to do is that I just subtract x star from both sides. X star, sorry. I'm going to first write x star is equal to x star plus alpha ax star minus b, right? So this is equal to 0. This is x star, so I can write it this way. Then I subtract the two equations, and what I get is something very simple that says xt plus 1 minus x star is I minus alpha a xt minus x star. Okay? Now let's think about the convergence of this algorithm, right? So what do we expect? We want xt to go to x star, so this one has to go to 0. And we want to see if it goes to 0 or not. And in order to make sure that we understand the problem better, let me do the spectral decomposition of A. So I'm going to write A as Q lambda Q transpose. What is this Q lambda Q transpose? This includes all the eigenvalues of my A. So this is a diagonal matrix that has all the eigenvalues of A. And these, I guess, Q transpose is a matrix that has the eigenvectors of A as its columns, right? So Q is concatenation of eigenvectors of A. Okay, so this is what we have now. And okay, so then I can also write, we know that this Q is going to be an orthonormal matrix because A is symmetric and it has all the nice properties. So I'm going to also write identity as Q transpose. And then I can just multiply both sides by Q transpose, and what I would get is Q transpose xt plus 1 minus x star is lambda Q transpose xt minus x star. You will see in a second why I'm doing this calculation. But I hope the calculation itself is clear. Okay, so what happens? I want to show that xt minus x star goes to 0. So let's say I'm interested in the L2 norm distance between xt and x star. Then since this is an orthonormal matrix, I know that the L2 norm of this thing is going to be the same as the L2 norm of xt minus x star. So I can just focus on this vector, right? So let me call this one vt plus 1, or let me just call it vt plus 1 here, is equal to lambda vt. And what I want to show essentially is that the norm of vt goes to 0. That's what I want to show. Everyone is with me so far? Any question? What's that? Oh, I'm sorry. I minus alpha lambda. Thank you. Okay. Now let's think about this one. What is the advantage of, so essentially what I have done here with this Q is that I take this vector and I rotate it, right? This is a rotation matrix, so I'm just rotating it, but because of this rotation, something interesting has happened here. Now I can talk about the convergence of individual elements of V. So I can say that, you know, Vi t plus 1 is 1 minus alpha lambda I, Vi t, and we can easily see the convergence of the algorithm coordinate-wise now, right? So every element of this one, since this is diagonal, I can just easily calculate the convergence rate. Okay, now here is the first question we should answer, and that is, how do I choose alpha? What is the right way to choose this step size? Because I have a freedom in my algorithm to choose the step size, so how do I want to choose the step size here? And here are the few things that we should think about, right? So if alpha is too small, then what happens? We see that everything here, let's say lambda i's are of course positive, everything here is going to be less than 1, and we will have the convergence, right? But the convergence is not as fast as you like, right? Because alpha, let's say the smallest eigenvalue, so let me just also assume that this is the smallest eigenvalue, this is the largest eigenvalue. If alpha is very small, alpha lambda 1 is going to be almost 0, so the coefficient that you're getting here is close to 1, the convergence rate is going to be very slow. So alpha very small, we can see that, you know, 1 minus alpha lambda 1 controls the convergence rate. And it is slow convergence in some sense. So if alpha is very small, it's very close to 1, the convergence is going to be slow. So that alpha close to 0 is not the optimal solution. You get the convergence still, but it's not great. Now let's increase alpha. So I'm going to increase alpha. And then as I increase alpha, okay, this term is getting bigger and bigger. So it seems that this thing is getting closer to 0 and convergence rate improves for a while. But then at some point, alpha lambda m is going to be greater than 1. And in fact, it's going to get closer to 2. So then this entire thing is going to get very close to minus 1. And again, the convergence rate is going to be slow. So for large, when alpha gets close to, yes.
Can you write the data bigger?
Oh, of course, yes.
Also push the board up a little.
Okay, sure. So let me just, oops. When alpha is close to 2 over lambda, the maximum eigenvalue, then alpha lambda p is going to be close to 2, and again, the convergence rate is going to be bad. So again, then convergence is slow. So what that means is that the optimal choice of alpha is somewhere between 0 and this value that is making that essentially slows down the convergence rate. So what is the optimal choice of alpha? As you can see, the two things that are controlling the main convergence rate is this term that is controlling essentially when this one is getting close to 1, and then alpha lambda p that is controlling when this thing is getting close to minus 1. The entire thing is getting close to minus 1. So if I want to get the best convergence rate, what should I do? I should just make sure that these two things are in balance, right? So for the best convergence rate, I set alpha in a way that 1 minus alpha lambda 1, the convergence, the smallest element here, is equal to minus, so the other one is going to be minus 1 minus alpha lambda p. And this essentially means that alpha is going to be 2 lambda 1 plus lambda p. More or less, this is the optimal step size that we have for gradient descent. Okay. So what is the convergence rate now? We can now calculate the convergence rate of the gradient descent. So the convergence rate becomes, essentially, you can easily see, so you can easily confirm that in this case, at least xt plus 1 minus x star is less than, this is the L2 norm, is less than lambda p minus lambda 1, lambda p plus lambda 1, xt minus x star. So you can just put this one in and then bound these elements easily and then get this thing. So this is what in convex optimization called linear convergence, because the mean square error in the next iteration is a linear function of the mean square error in the previous iteration. So we call it, they call it linear convergence. And now let's interpret these results and then answer some of the questions. So there are some questions about our analysis. So these are the basic questions we should ask. Does this result make sense? So does it intuitively mean, do we think that do we intuitively think that this should be correct, right? So is it consistent with our intuition? So that's the first question. And of course, the second question is it a sharp analysis? Sharp analysis. Right? So for the intuition, I mean, something that we may think about is the following two situations, right? So I have, let's say in one case, the A matrix is equal to identity, and let's say B is equal to 0. And in the other case, A is going to be equal to 1, 10, 0, 0, B is still equal to 0. So if I plot, if I do the contour plot for X transpose AX in this case, everything is circular, right? So it's going to be something like this, right? These are the contour plots for X transpose X essentially, because A is equal to identity. For the other one, let me think. Yes, it's going to be kind of ellipsoid. Okay. So if you look at the gradient descent here, what does it do? So it moves in the direction of the negative gradient. So it's going to move in this direction. And as you can see, the direction of the gradient descent is actually correct, right? So the direction of the gradient descent is toward the center, that is the minimizer. So that's why if you look at this algorithm, it tells that if you pick the optimal choice, you go to this point in one step, which is great. So this is very good. And gradient descent, I mean, is optimal here, right? This is the best thing you can do. But now, if you are in this case, which is an ellipsoid, okay, I'm sorry, I guess many people cannot see this, which is an ellipsoid here, then what does the gradient descent do? Okay, again, it tries to go in the direction of the gradient. So this is the direction of the gradient. Let's say it goes this way. Then it hits here, right? So it's going to go again in the negative gradient. So it's going to go here, here, here. So you see that it starts zigzagging, right? In this case, it seems like doing optimal thing, but in this case, it's just zigzagging toward the center. And why is that? Because these things are, you see the eigenvalues of this matrix are, the condition number is quite large, right? The condition number is large, so gradient descent is doing the zigzagging. And if you think about it, that is exactly what this suggests, right? So it says that if lambda p to lambda, so let's say the convergence rate is something like this. So if lambda p to lambda 1 is very large, if this one is very large, then you can ignore this term, and essentially the convergence rate is very close to 1, so gradient descent is not going to perform that well. So it really depends on the condition number of the matrix. So far, so good. Any question here? Yes, please.
Is it possible with this technique to accidentally get to maybe just a local minimum?
So we are here in the convex setting, right? And then not only convex setting, I'm actually making assumption about the strong convexity that I'm going to mention. So the solution is unique. And no, there is no way that it gets stuck in anywhere else. Okay. So this is a very basic analysis, but it reveals a few things about gradient descent. Can we generalize this to more general settings? Of course, it's very easy. The ideas are simple. So let me just mention the generalization of the proof, and then we move on to stochastic gradient descent. So how do we want to generalize the idea? I mean, as you can see, let me just keep the analysis here. The rest are not that important for the general setting. So this is a more general setting. I have to make a few assumptions about the function itself, right? And in this talk, throughout the entire talk, I'm going to make these assumptions about my functions just to make the presentation simpler. For other cases, you have to do a little bit more work. So what are the assumptions I'm going to make? So these are the assumptions about my function. Okay, this is the gradient descent first. Let me just mention xt minus alpha t gradient f of xt. This is my function. Now I want to make 3 assumptions about this function. What is the first assumption? Okay, let's say f is twice differentiable. That makes life easier. The second assumption, okay, so we saw that in this quadratic case, the eigenvalues of A really mattered, right? So the minimum eigenvalue and maximum eigenvalue were the things that were controlling the convergence rate. So and what is this A? This is essentially the Hessian of the function, right? So A is the Hessian of the function, So I really want to put constraints on the eigenvalues of the Hessian, exactly the same as what I did for the quadratic case. So let's say lambda max, this is another assumption that I'm going to make, of the Hessian of the function at any point x. I'm going to assume that this is less than L. L is a fixed number, so L, a fixed number. As you can see, it's inspired by the quadratic case, right? So that's why I'm focusing on Hessian, and then I put a constraint on the maximum eigenvalue. And of course, I want to also impose a constraint on the minimum eigenvalues. So lambda mean Hessian of x is greater than mu. Okay. how do we do the analysis? The analysis is really simple, right? So again, we do the second equation. X star is x star minus alpha t, a gradient of f at x star, because the gradient of f at x star is going to be equal to 0. Then I'm going to subtract these two. So it's exactly. This is just strongly convex setting throughout the talk. So I'm not going to. I'm going to mention that some of the things that we are not covering, but that's essentially what we are going to focus on. So okay, so what do we get? This is essentially a strong convexity. This is what we call strong convexity assumption. And this is a smoothness assumption, right? So I'm not letting the Hessian to be very large. So it's more or less like another smoothness, extra smoothness assumption about my function. Okay, the analysis, as you see, very simple and very similar to what I had before. So xt plus 1 minus x star is going to be xt minus x star minus alpha t, gradient of f of xt minus gradient of f of x star. Okay. Now, okay, so I want to do what? I want to somehow connect it to the Hessian of the function, right? Like this is very similar to what I had before. A xt minus x star. A more or less represents the Hessian. How can I do that? At the intuitive level, what do you know about this term? A gradient minus gradient, right? Or let's say, what I want to claim is that, you want to write it as the Hessian. You really want to write it as a Hessian at some point times xt minus x star, right? If I could write it in this way, if I could write gradient minus gradient in terms of the Hessian and xt minus x star, I would be in a very similar situation as the one that I have here, right? And this should remind you something like the mean value theorem, right? So the mean value theorem, let me just write it here for those of you who don't remember, says that at least for, let's say, f from R to R, f of x minus f of y is equal to f prime of some point in between x minus y. So this is what is called mean value theorem. So you were hoping that even for vector valued functions, you would like to write something like a mean value theorem. And that's exactly the right strategy, right? Except that the mean value theorem is not of this form anymore, right? So let me just write the mean value theorem, and then I will leave the rest of it to you to do the calculations. So this is a vector valued function, so the classical mean value theorem cannot be applied to it. The integral form of the mean value theorem, however, applies to these things. And what is that? It says that, this is essentially equal to the Hessian of f, let's say, at x star plus some gamma xt minus x star d gamma from 0 to 1 times xt minus x star. So instead of just putting the Hessian, we wanted to put the Hessian and then get it back to the form that we had for the quadratic functions. But now I have to deal with this integral, but nothing really changes here, right? So I don't, you can think about it. So what you can see is that we can do exactly the same things that we were doing before, right? So I'm going to take everything essentially inside the integral, And then I have a bound on the eigenvalues of the Hessian, so I can easily bound these things. So for instance, you can just see that, I can just write xt plus 1 minus x star is equal to integral I minus alpha t gradient of f x star plus gamma xt minus x star d gamma. And in fact, actually, I can even take xt minus x star inside d gamma. And then you take the L2 norm from here, right? You take L2 norm from here minus x star. So you can just take the L2 norm inside, and everything then is going to be the same. Essentially this. So I'm going to leave it to you to do the calculations, the rest of the calculation, but everything is going to be the same as what we had before. You can just set alpha t to what we said before, 2 over the mu plus L, and then you get the convergence rate that we wanted. Okay, so this is about the standard gradient descent in case of the strongly convex. And we have to talk about a few things here. So the first thing would be, can we improve the convergence rate by better theoretical analysis? And from the quadratic setting, you can say that no. In the quadratic setting, that was the best step size. If you check the analysis, everything is quite sharp in the analysis. So there's no way we can improve the convergence rate of the gradient descent for these type of functions, right? Now, the second one is about optimality that we asked before. So is gradient descent optimal? And the answer is no. Let me just elaborate a bit on it, and then we move on to gradient descent. Sorry, the stochastic gradients. Any questions so far? Everything's clear? Okay. So the way people talk about optimality in these cases, it's going to be slightly different from the optimalities that we will see in the stochastic gradient setting, is the following, right? So this is the strategy that people use. So the idea is the following. So how do we define optimality here? And I think the idea of defining the optimality in the way that I define here goes back to Nemirovsky and Yudin. And they defined the optimality in this way, right? So they said, let's focus on the first order oracles. So what that means is that I have an oracle, and this oracle is able to give me the gradient information every time I give the oracle x. I give x, oracle returns gradient of x, gradient of f of x. So this is our oracle. And let's say, suppose that I call the oracle I can call the oracle t times. Okay? So I'm allowed to choose x1 to xt. I'm allowed to x1, xt. Give it to oracle. Oracle is going to return to me gradient of f of x1 to xt. So oracle returns gradient of f at x1 to gradient of f at xt. So that's what oracle does for me. Now, the question is, based on this information, what is the best estimate I can get for x star? Okay, so I'm calling oracle t times in any way I like. I get this information. I can combine them in any way I like. And the question is, what is the best accuracy I can get here, right? And the way we see it is this one, right? So I'm going to define a class of functions. So let's say class of functions. For example, I'm going to say f from Rp to R. Let's say P is a really large number for now. F from Rp to R, such that, you know, the f twice differentiable. The Hessian of f at any point x, if I calculate lambda max of this, the maximum eigenvalue, this is going to be less than L. Lambda mean of the Hessian is going to be greater than mu. So I'm going to look at this class of functions, let's say f, and I'm asking, okay, so let's say based on this information, I come up with an algorithm that gives me, so let's say I have x star. My algorithm is going to return, this is my algorithm, uses the x1 to xt, f of x1 to f of xt, and gradient of f of x1, gradient of f of xt, to give me an estimate of x star. So let's say this is the error that I have now, right? So this is my algorithm, this is what it does. I'm going to say, you know, I'm going to try to find the supremum over f in calligraphic f, infimum over all the algorithms. Does this make sense to everyone, what we are doing? So we want to make sure that the algorithm that you give me, it's gradient descent, it's something else, it works for any f, so I'm going to take the supremum and I'm going to get this algorithm. X star depends on f, exactly. Right, this is the optimal of the f, let's say, right? Okay, when you phrase it this way, this looks like a complicated thing to characterize, right? But it turns out that these things are very, okay, reasonably easy. The idea is that usually, at least the lower bounds that we have in many of these cases, are based on quadratic functions. So I'm not going to get into the details, but let me just give you the idea. It will take at least 20 minutes to do it completely. But the idea is the following, right? So instead of focusing on all these f's and so on and take supremum and whatever, you focus on very simple functions that are x transpose ax minus b transpose x. But then you somehow construct A in a very specific way so that you can control the direction of the gradient. So you can control the direction of the gradient at every iteration, so the algorithm cannot go in any direction that it likes, right? So it's going to focus on a very specific directions, on very specific directions. Right. So let's say x star is something that we want to get to, depends on f, right? So let me call it x star f. This is the optimal of the f, the optimal value of the f. And then I have an algorithm that uses your iteration so far. x1, let's say you got x1, then you learned x2, then you learned based on gradient and so on and so forth. You got to this stage, right? So it uses all this information. So gradient descent only use gradient at time t, right, to get to t plus 1. But this algorithm is allowed to use all the gradient information that you have so far. And then it gives you an estimate of x star. Now the question is, how close is it to x star?
So that's the first order.
And so it. It's not first order expansion, right? So you have the value of the function gradient at many different points, right? Exactly. So let's say this is your function now. So you are getting the gradients at all these different points now because of your iterations, right? And then the question is now I allow you to use all these other things, right? So I'm going to allow you to use all these other things to somehow get a better estimate of this optimal. And hopefully this should be sure, okay. Okay, so that's a good question. So let's say x1, when I'm talking about, I can start from some x0, right? So x0, I give it to the oracle, get gradient of fx0, f of x0, right? Based on these things only, I have to come up with x1, right? Then x1, I can give it to oracle, fx1, f of x1. Then based on the entire thing now, unlike the gradient descent, now I can use the entire thing to come up with the next system, and so on and so forth. So this is the way I'm coming up with this next system.
Just one quick question. The way you're defining the minimax, so x1 through xt is actually chosen by, okay, x1 might be chosen, but
right, exactly.
Because you have them as
That is fair. I guess my notation is very bad. I agree.
So really, it's just access to the first order information theta.
Exactly. In a kind of sequential manner.
And, but is the initial points conforming the minimax?
So that's a very good point. So the way, if I want to write it more carefully, at least from the proof, what you see is that most of the lower bounds are generated for a specific initialization, right? So you construct a function in a very specific way, then you tune the initialization for that function, and so on. So it's not that, if you give me a function and say, I'm going to randomly choose the initialization, these lower bounds, at least the proofs do not work that way.
Okay.
At least I don't know if they work that way.
So the minimixity here is with respect to an algorithm that's given an initial point.
Exactly. Initial points of my choice, the adversary choice. Exactly. There was another question, no? Okay, so now that's about the lower bound. Now what do we get from these things? The lower bound that is proved by, I think, again, Nemirovsky, or maybe, I think it is in Yudin and Nemirovsky book. I haven't checked, but I think it's there. The lower bound that we get based on this says that essentially for any first order method, xt minus x star squared is greater than or equal to square root L over mu minus 1, L mu plus 1, xt minus x star. So if you compare it with what we had for gradient descent, so for gradient descent, this result was the ratio of the eigenvalues, so xt minus x star was less than L over mu minus 1, L over mu plus 1, xt minus x star. Did I do anything wrong?
I mean, the right-hand side should not be based on xt. Right?
Oh.
0 or something.
Exactly. So this is, I meant this xt plus 1. So that's, sorry, this is x. Just give me 1 second. Is this correct now? So the next iteration based on the previous iteration. There was a. No, so this is a lower bound, right? So it says that for any algorithm, so this is for any first order algorithm, you can't do better than this. So this is actually greater than or equal to. This is a lower bound, right?
It looks wrong. Yes,
Mm-hmm.
The step xt is not good, but xt minus 1 was a better approximation, and the algorithm throws xt away. Your lower bound depends on xt.
Right.
But I mean.
But this is like optimal thing, right? So at every iteration, you are doing the optimal thing. So it's not going to happen that you're doing a bad thing from xt minus 1 to xt because you're doing the optimal thing.
For every function?
And not every function. No, of course not. So this is supremum over the functions, right? For the lower bound, right? So we are constructing a very specific function, right? If you want to check it, for example, usually these functions look like x transpose ax when x is something very sparse, right? For example, it's going to be 2 minus 1 minus 1, 2 minus 1, something like that, so that you can really control the gradient and make sure that the gradient doesn't move in a very cannot move in every direction, right? So this is for very specific function. You calculate this lower bound. So there are lots of criticism that you can have about this lower bound, right? For reasonable functions, it might not be necessarily meaningful. Another criticism that you can have is that this is given for you kind of tailor the initialization to the function. So if you randomize the initialization, I don't think we have necessarily a lower bound again here. So there are lots of things that you can argue here, right? But at least it says that you can have, it seems that you can have an algorithm that reaches this one for every function. So far so good? Everyone is okay? Okay. Now, okay, so what can we do? What is next, right? So it seems that, yes?
So is there any lower bound that is actually directly not in terms of any step, but in terms of convexity to
Right.
to x star itself?
Right. So you mean like you want this one to be 0?
To be 0, yeah.
I guess this becomes like t. Yeah, exactly. There is this lower bound. So you can yeah, and the same here, right?
I mean, the upper bound is convertible to that I agree, but I'm just wondering whether the lower bound is convertible.
Exactly. So one thing that I should mention about this thing, right, is the following. As I mentioned, the lower bound is constructed based on these scenarios, right, that I have a matrix. So in order to make sure that it holds for every t, every step t, they have to essentially make the problem infinite dimensional. Because after a while, at every step, your gradient information is going to add one coordinate to your search space, right? And if this is a p-dimensional problem, after p iterations, you have all the coordinates. So this lower bound is not going to work if you work on a p-dimensional problem. So in order to make sure that it's working for everything, they let the dimension go to infinity, right? So if you're looking at this thing and then your t is larger than p, it doesn't mean anything. I don't think this lower bound at least doesn't. The lower bounds that I know do not hold. I'm not sure if people have studied this thing. Make sense? Okay, so what can we do about this issue? I mean, this is something that people knew more or less. They had the idea more or less from 1950. And the reason was that people were trying to solve linear problems. And when you solve the linear problems, let's say ax equal to b, you more or less have the same issues, right? It's essentially the same as gradient descent. And back in 1950, back in 1951 or 1952, conjugate gradient was proposed, and conjugate gradient was able to solve linear systems at this rate, right? So from that year, people knew that there should be some way to improve the gradient descent, right? So this is the idea that they had from 1950, and they tried many things. But let me give you the intuition first, because I guess I spent too much time on convex, which is not the focus of my talk, actually. So the idea people had was very, very simple. So the idea that people had was very simple. So the issue is, of course, when these ellipsoids are very narrow, or mu p or L over mu is very large, right? If L over mu is very large, as I mentioned here, you see that this is L over mu. This is a square root L over mu. So the lower bound is much better, right? So, and then people said, you know, what is the problem? Why is this happening? Because we are greedy, and at this point we move in this direction of gradient. So we go here, and then here we see the gradient again, so we move in the opposite direction. So this moving in this direction and then opposite is something that makes gradient descent very slow, right? Because every time we are very greedy, we just look at the gradient, we move in the direction of the gradient, and we forget about the past, right? But if, for example, I looked at the gradients from this iteration and the previous iteration, I would realize that, okay, I'm going back and forth, so I could take the average to get a faster convergence. So far, so good? So these ideas were around in convex optimization from, I guess, 1950. It started with conjugate gradient, and they are usually called heavy ball methods. So the heavy ball methods had this idea that instead of updating with the gradient, so this is what we had in gradient descent, I'm going to do this. I'm going to update my xt with another vector, which I call it dt. And then dt is going to be dt some beta, dt minus 1 plus beta bar, or 1 minus beta, the gradient of f at xt. So these heavy ball methods existed for a long time. As you can see, by taking the average of the gradients, you are hoping to avoid this issue of going back and forth. And in practice, they usually work better than gradient descent, right? And finally, in 1980, Nesterov. So one of the issues that people had before 1980 was that they knew that these heavy ball methods are working better than gradient descent, but they didn't know how to prove that they are doing better, right? So around I guess it was 1982 maybe, or 1998, that Nesterov came up with a specific recipe for heavy ball methods for which he could prove something like what we had in the lower bound, right? xt plus 1 minus x star L2 norm is less than L over mu minus 1, L over mu plus 1, xt minus x star. So this is the more or less what we have on vanilla gradient descent. Let me just mention some of the things that I haven't covered, and then I just the next time we come back, I'm going to start with the gradient descent. So something I haven't talked about is, of course, any questions so far? Yeah.
Is this recipe just a choice for beta?
It's actually more complicated than that. It's slightly more complicated than that. It doesn't use exactly this type of heavy ball method. For example, one thing that he does is that all of these things are changing iteration by iteration. So he's even changing these ratios. Okay, so that's it. Now there are lots of things that we can talk about, right? In convex optimization, I just talked about minimizing f of x when x is in RP, right? Now you can imagine that lots of things can be said when it's a convex set. So it's we want to minimize over a convex set. This is another set of problems, and then lots of interesting things happen here. Then we can talk about the situations that we have two functions. For example, one of them is differentiable, the other one is not differentiable. That's a different, again, a different set of algorithms. But most of the things, as you can see, if you learn one trick, then everything comes back to what we have here, right? So that's why I just focused on this class of problems. Okay, we're done. I guess the next time we come back, we are going to be.
Yeah, should we
So
come
yes,
back
okay.
and